Good morning one and all. Today I am discussing about Orifice meter apparatus which is used to calculate coefficient of discharge. So in the fluid mechanics and hydraulic machinery laboratory subject under subject code 18CVL48 for module 1 and lecture series 4 to 6 semester civil engineering students. To study the above flow measuring devices and to determine the coefficient of discharge of the orifice meter, the aim of today's experiment is to study about the flow measuring devices and to determine the coefficient of discharge of orifice meter. The apparatus required for here is a frame, a monoblock form, sump and a measuring tank, a balancing tank, test section with piezometer pipes and valves and other accessories. So in one sentence, if we want to say the orifice meter is an orifice meter is a simple device used for measuring the discharge through pipes. So coming to the formula, the entire experiment is to calculate coefficient of discharge to orifice meter CD, which is equal to Q actual, that is actual discharge, divided by Q theoretical, that means theoretical discharge obtained from empirical formula. So now we have to calculate actual discharge and some of the input data we have to take to substitute in theoretical discharge formula to calculate the end result coefficient of discharge. Coming to the determination of actual discharge Q actual. Q actual is given by A into H divided by T. What is meant by A? Area of the collecting tank, L into B. H means the rise of water level in the tank for a given time interval or for a constant rise of water in that measuring tank, how much time it takes that we have to record. The time is in terms of seconds. Okay, generally we are doing this experiment by considering 10 centimeter rise or 100 mm rise in the tank, how much time it takes in seconds. So coming to the Q theoretical discharge. Q theoretical discharge is given by formula. So K naught into root of 2G H naught, where K naught is called as an orifice constant, which is equal to A1 into A2 divided by root of, this root will up to this end, root of A1 square minus A2 square. What is A1? A1 is nothing but area of the orifice meter at entry. So point, so in meter square, which is given by the circular pipe diameter pi d square by 4. So where D in our laboratory, so R in most of the model tanks will be 0.027 meters. The area of the orifice meter at Venturi Vena contracta is A2 pi d square pi d2 square by 4, where d2 is 0.015 meter. So I wanted to say an example here. So this is assume that this pen is a water pipe. So there is a slope in this pipe, there is a contraction in this pipe. Let us forget about this pen entire length, consider this length, assume that there is a one more pen is here. So this area of cross section at this point is A1, whereas at the vena contracta, that is the tapered end portion, so is D2. So this diameter at here is D1, you can see in my finger, here is D1 and here it is D2, here is 0.027, here is 0.015 meter. So substituting the A1, A2 in the Orifice constant K0, which is equal to A1 into A2 divided by root of A1 square minus A2 square will give the K0, which is called as Orifice constant. Next, so G is acceleration due to gravity, that is known to us, and H0 we have to calculate. What is meant by H0? H0 is nothing but manometer head for Orifice. So the H0 is given by formula H1 difference H2 divided by unit conversion from that is the millimeter to the meter into rho into Hg divided by rho W minus 1. So where H1 is initial height of the liquid in manometer, H2 is the final height of liquid in manometer, rho density of mercury divided by density of water. So if you substitute that these values, you will get H0. Substituting H0 here, this root of will be up to the end, 2G into H0, you will get the, so Q theoretical for one trial. So the coefficient of discharge for Orifice meter, Q actual divided by Q theoretical, if you do it, you will get the value, that is coefficient of discharge through vertical Orifice meter. Coming to the procedure part, so note the first procedure is note down the dimension of the measuring tank. So we will have a measuring tank, that measuring tank L and B, I will show you in the next slide, that L and B we have to measure it and you have to record it. Open the discharge valve, wait for few minutes so that the flow becomes steady. So the moment if you open it, there will be a air bubble will be there, that air bubble will not make the flow become laminar. So if you leave it for some period, release of all the air bubble will makes the flow become laminar. So once it become laminar, a steady flow will occur. Then note down the measuring levels in the left and right column of your U-tube manometer. So that left column reading is H1, capital H1, right column reading is capital H2, and H0 is H1 difference H2. Close the outlet valve of measuring tank and note down the required for 100 mm rise in water in the piezometer. Okay, so the time required for 100 mm water in the rise in the piezometer is to be recorded. And repeat this procedure for different discharge. What is the meaning of different discharge? That means this is your pipe and there will be a valve will be there. So if I open this valve, it is 100%. If I open this one, so it is a 75%. If I rotate like this, 50%. If I rotate like 25, if I rotate is 100% closing take place. That means if the valve opening are various, that is flow rate you have to maintain it. That is you can start with 25% opening to 100%, or vice versa you can do it. Then calculate the coefficient of discharge. This is one is analytical method, another one is graphical method. So by plotting the graph, for plotting the graph we are using Q theoretical discharge versus Q actual discharge values. For that minimum 3 discharge range we have to consider. Okay, 25%, 75%, 50% or 50, 75, 100%. Next, so this is a instrumental setup which is present in the government Sri Krishna Rajendra Silver Jubilee Technological Institute, KR Circle, Bengaluru. So according to this instrument, most of the college will also have a model prototype like this. So this instrument is a combo instrument composed of Orifice meter, Venturi meter and rotometer. Okay. So now coming to the point, okay, so here we are written O, here we are written V, here we are written, so O, here we are written O, that is the entire thing. So it's a two purpose it is used. So here wherever V is there, so that V is an indication that is the Venturi, here V and V, and here O and O is there, that is Orifice meter. So this is your Orifice meter, that is assembly, where you have manometer here. Okay, so this is the measuring tank. Whatever I said, L into B is the measuring tank, and here there is a change in the diameter of the pipe take place at this point, and this is connected to the some fund pumping arrangement. So if you can see here, at this point the diameter is D1. At this point, so at this throat point, this is called as a throat point. The magnified one in case of Orifice, you can see here, this is throat point. Similarly here also there is a one throat point. At this throat point it is D2. Okay. So now let us take a small that is example in order to convince the students community about how we have to do the calculation. I have taken only two trials. Okay. So the first trial, when you switch on the motor, when a steady state condition has occurred, then so flow of water take place, and when once the flow of water take place, whatever manometer reading is here, if H1 you are recording, manometer reading is here, H2 is recorded. As it is very small, so sometimes reading the H1, H2 is very difficult. Therefore, it is these pipes are connected to a one more manometer board here. From that, so you can record directly what is the level of U-tube manometer, one side H1, another side H2. Okay. Afterwards, there is a that is the tank, collecting tank. The tank is fitted with a that is the piezometer. So what we have to do is, for 10 centimeter rise in this piezometer, below the photo we have that one, 10 centimeter rise in this tank, how much time it takes, that we have to record it. Now let us see with a typical example how these calculations has to be done. H1 is 39.4 mm. Okay. So as I said here, as this is a very small manometer, it is connected to this manometer board, where we will get a, in a tube, magnified values will get it, that we are recording here. H1 39.4 mm, H2 is 39.6 mm. Okay, because here the variation may be high, but when you fix to the board, the variation is less, because there is a huge magnified length has taken, that everything is calibrated, we need not necessary to worry. So therefore we are getting small variations, so that is around 0.2. and for rotometer, so it will gives the rotometer reading, that is 10, and then Q actual is AH by T. As I said earlier, A is cross-sectional area of the tank, H is rise in the water, and T how much time it takes. Okay, so that reading we have to substitute it, we will get this value. Then H0, H1 difference H2 divided by 1000, rho GH by GW minus 1, you will get in meter. Q theoretical is K0 into root 2G H0. So in meter cube per second you will get Q theoretical, Q actual by Q theoretical will get the value. Okay, average, first reading, second reading will get it, average of this one will get this CD average. Okay, so now Coming to the multiple choice questions, the Orifice meter is a cheaper arrangement for discharge of measurement through a pipe, and its installation required a small length as compared with the Venturi meter. Whether the statement is true or false. So option A is true, option B is false, option A is true. Actual discharge Q actual is equal to AH by T through the orifice plate. So option A is true, option B is false. Our answer is option A, because actual Q actual will be determined by using AH by T, whereas Q theoretical will be determined by using K naught, so into 2GH. Okay. So next is manometer head for H naught. Manometer head of orifice meter H naught in the orifice plate is H naught is equal to H1 difference H2 divided by 1000 into rho of density of mercury divided by density of water minus 1 in meter. Option A is true, option B is false. Correct answer is A, it is true. Orifice constant K naught is equal to A1 into A2 divided by root of A1 square minus A2 square. So this formula is correct, therefore option A is true. Theoretical discharge measured through a orifice meter K naught into root 2G H naught. Option A is true, option B is false, option A which is true. Next, to calculate the coefficient of a discharge through orifice meter, Q actual divided by Q theoretical, that we have to use it. So Q actual by Q theoretical, therefore option A is true. So manometer head, so reading for an orifice meter H naught in orifice plate is H1 difference H2 to the 1000. Density of water by density of mercury minus 1. This formula is wrong, because density of mercury is 13.6, whereas density of water is 1. If I 1 divided by 13.6, if I do it, you will get a decimal value. Minus 1 is again negative value, that means your H naught will be negative. So question may be very simple, but logic behind the question framing, if you understand, you can never get a H naught is negative. What is meant by H naught negative? H naught negative means H1 difference H2 is minus, that means minus H1 plus H2. So before starting the experiment, your H2 value should be higher than the H1 value. That here practically it is not at all possible, therefore this equation is wrong. So our option is B, which is false. Coming to the orifice constant K naught, K naught is equal to A1 divided by root of A1 square minus A2 square. So when you want to say orifice constant, you should compare the cross-sectional area at the inlet point and also at the throat point. If we consider alone inlet point alone, it cannot be determined, because throat is the place where the decrease in the diameter takes place. Without that, constant cannot be determined. So constant can be obtained only if you have two parameters. Therefore the statement is false. Theoretical discharge measured through a orifice meter K naught into root 2 H naught. So here the equation will not get balances if you don't substitute acceleration due to gravity value. That means without gravity value, this equation is an imbalanced equation. Hence the statement is false, the equation is wrong, and answer is B, which is false. The manometer head of orifice meter H naught in meter in an orifice plate is H1 difference H2 divided by 1000. The purpose of dividing 1000, or the purpose of here in this equation divided by 100, is not simply writing a numerical value. It is converting the millimeter to a meter. So from millimeter to millimeter means decimeter, centimeter, so decameter, they are millimeter. So millimeter to meter means millimeter, centimeter, decimeter. Therefore it should be divided by 1000 here. So it is divided by 100 is there. So it is not correct. So in order to substitute in the Bow equation, therefore the statement B, which is false. So these are all the list of book, that is one Bansal book used, R.K. Bansal, for preparation of this particular material, and the photograph shown is the courtesy of the Government SKJP Department of Technical Education, Care Circle, Bangalore 1, Fluid Mechanics and Hydraulic Laboratory, existing equipment photo. I take this opportunity to thank Department of Collegiate and Technical Education for giving me an opportunity to deliver a laboratory related lecture in LMS portal. And also I take this opportunity to thank all the students across Karnataka from all government engineering colleges for listening this lecture. If you have any doubt related to this particular experiment, so you can ask in the next class. I request all the students to log into the LMS portal and utilize the study material, PowerPoint presentation, MCQ question and video uploaded with respect to this subject. Thank you for attending the class. Thank you.